All right, let's get straight into it. Today, we're going to break down a really challenging 13-mark GCSE physics question. I'm going to show you exactly how to tackle every single part, step by step, using the official mark scheme so you know how to lock in every possible mark.
So, why this one question? Well, it's worth a huge 13 marks, and it's all about the motor effect, a massive topic in GCSE physics. We're going to look at exactly what the examiners are looking for, from the way you explain things to how you lay out your calculations.
The question we're about to dissect is question 09, and it comes from the AQA GCSE Physics Higher Tier Paper 2. It's a real classic, a problem that's designed to test a whole bunch of your physics skills at once.
Okay, so first, let's get a picture of this setup in our heads. You've got a copper rod, and it's sitting right in a magnetic field. It's also wired up to a power supply. The moment that switch is closed, current starts flowing, and bam, the rod starts to move. That right there is the motor effect in action. Right, the first part of this question is a big one. It's worth 5 marks. And it's all about explaining why and how that rod moves. So this is asking for a quality explanation, not a number. So the question is super specific. It says, explain how Fleming's left-hand rule can be used. See that? It's not just asking which way does it go. It's asking for your method, your process. Every step you explain correctly is another mark in the bag. Okay, let's dive in. This is literally the perfect 5-mark answer taken straight from the mark scheme. First, you just describe the setup, get your left hand out and hold your thumb, first finger, and second finger all at right angles to each other. Step 2, you point your second finger in the direction of the current, which the diagram shows is coming out of the paper. 3, you line up your first finger with the magnetic field, so pointing downward. Now, here's the magic. Your thumb is now automatically pointing in the direction of the force. And for that final 5th mark, you just state the conclusion. The rod moves from left to right. Done. Simple enough, right? Let's keep the momentum going and move on to the next part. This one's worth 2 marks, and it's about making some practical changes to the experiment. The question's pretty direct. What are 2 things you could change in the setup to give that rod a bigger push? The mark scheme gives us a few options for this one. Okay, for your first mark, you could say decrease the resistance of the variable resistor. And that makes sense, right? Less resistance means a bigger current can flow through that rod, and a bigger current gives you a stronger force. The mark scheme also says you could just be more direct and say increase the current or increase the potential difference. Any of those gets you the point. And for the second mark, you can just say use a stronger magnet. It's pretty intuitive. A stronger magnetic field is going to give a bigger push on that wire. Now, if you want to sound a bit more technical, the mark scheme also loves the phrase increase the magnetic flux density. Both get you the mark. And now, for the main event. The final part is a huge 6-mark calculation that pulls together a few different physics equations. For a question like this, showing you're working nice and clearly is absolutely everything. So here's our mission. We've been given a whole list of values, and we need to work out the final speed of the rod. This is a multi-step problem, so the very first thing we have to do is get our information organized. Let's lay out all the data the question gives us. We've got time in seconds, current in amps, mass in grams, length in meters, and magnetic flux density in Teslas. Seeing it all in a table makes it much clearer what we're working with. But hang on, did you spot the classic exam trap? And there it is. This is so important. The mass is in grams, but for our force and acceleration formulas, it has to be in kilograms. So we convert 4.0 grams to 0.0040 kilograms. Trust me, forgetting a simple unit conversion like this is one of the easiest ways to lose marks, so always check your units before you start. Our first calculation is to find the force that's actually pushing the rod. For that, we use the motor effect equation, force equals B times I times L, or MEG, magnetic flux density times current times length. So let's just plug in the numbers we have. The force is 0.3 times 1.7 times 0.050. Punch that into your calculator, and you get a force of 0.0255 newtons. And just by showing that calculation, you've already secured the first couple of marks. Nice. Okay, now that we have the force, we can figure out the rod's acceleration. And for that, we're going to use an old friend you definitely remember, Newton's second law, F equals m times a. First, we just need to rearrange the formula to find acceleration, so a equals force divided by mass. Now we can pop our numbers in. That's the 0.0255 newtons we just found, divided by our correctly converted mass of 0.0040 kilograms. That gives us an acceleration of 6.375 meters per second squared.
We're on the home stretch now. This is the last step. Because the rod started from a standstill and accelerated at a constant rate, we can use a really simple equation of motion. The change in velocity is just the acceleration multiplied by the time. All right, let's plug in those final numbers. The velocity is our acceleration, 6.375, multiplied by the time, 0.15 seconds, and that gives us our final answer, 0.95625 meters per second. Now, the mark scheme is fine with you rounding to 0.96 or 0.956, but showing the full number is perfect too. And that is how you get all 6 marks for the calculation.
And we did it! We've worked our way through all 13 marks. So before we finish, let's just quickly recap the key skills that got us here.
This slide pretty much sums up how you ace a question like this. You have to know how to apply Fleming's rule step by step. You need to remember the 2 key things that make the force stronger: current and magnetic field strength. You absolutely have to check and convert your units. And finally, you have to follow that logical path through the calculation. Use what you have to find the force, then use the force to find the acceleration, and then use that to find the velocity.
So we've nailed the exam question, which is great. But let's end with one last thought. This whole principle, the motor effect, it's not just something in a textbook. It's the engine that drives electric motors everywhere, from the fan in your room to drills and even electric cars. So the question to leave you with is, where else in the world around you is this fundamental principle of physics making things move?